Assalamualaikum and a very good morning. Uh, my name is Faizul. I'm from University of Malaya, Malaysia. Anyone have been visited Malaysia? Anyone? No? Nobody visited Malaysia yet? Anyone knows about University Malaya? Have you heard about University Malaya? Okay. Okay. Little bit the background of myself before we begin with our lecture, our course content. And I completed my bachelor from mechanical engineering in Japan. Then I completed my master's in Japan as well. Then I completed my PhD also in Japan. So even though I am Malaysian, but my studies all in Japan. And sometimes people mistook me as a Japanese or Chinese. I'm not so sure. I think I have one student from India. His name is Manoj. He's doing PhD under my supervision. And he said that first when he saw me, he think that I am Japanese because he see that my background study also in Japan. So I'm not sure. Okay, and okay, my involvement in MEMS started when I did my PhD, and before that, I have some interest in small scale things where I did my master's also in precision engineering. I think for mechanical student, you are familiar with the terms precision, right? Precise and accurate. So we try to machine something to be precise and accurate. That is about precision engineering. Then after that, I've developed some interest in further looking into small things where I started to look into microfabrication, or in some other terms, we call it MEMS, micro electromechanical systems. I've been working with University of Malaya since 2002, and it's quite some time ago. And my research interests are in MEMS devices, on the fabrication and also on the device design, and as well as I look into materials as well, because when we started with MEMS, we also look into the properties of the material. So with that knowledge, I try to develop some new materials which, according to whatever properties you required for certain application, for different application, then we try to develop the materials. It can be started from design of the materials itself using software. So it's quite easy nowadays because you have hypothesis, then you can simulate to see the properties, whether it's whether your properties will be right or not at a certain extent. And I look into energy materials called thermoelectric. If you are familiar with, anyone familiar with thermoelectric? No? Have you heard of thermoelectrics? Okay. Okay, maybe later on I will introduce a little bit on the thermoelectric materials as well, and piezoelectric. Anyone? Piezoelectric? Okay, piezo is more common, right, than thermoelectric, because piezo you convert the strain or the change in terms of the materials dimension into electricity. They provide strain and you can harvest electricity, and if you provide current or what you call it, a voltage, then you can get the expansion. The materials become actuator. So that is piezoelectric. So I work in piezoelectric as well as thermoelectric and another materials, which is pyroelectric as well. So that is, and also I work with solder alloy. If you are familiar with solder alloy, you want to have electronic packaging, you need to connect the electric circuit, then you have to have solder alloy. So that is part of my work. Okay, I think that is a little introduction. Let's begin with the course. It's 11:30, and okay, the course is about microfabrication techniques and device integration. So for mechanical background student, normally when you say microfabrication, you might have the imagination of having small drilling, of having milling of small things. So all about mechanical process, removing things, removing materials to shape certain objects with a mechanical process of cutting, milling, lathe maybe, and drilling, etc. With force. So that is what we normally as mechanical engineer have in mind. But for this course, we will go beyond that, which is more on the semiconductor process, which involve wet removal using chemical process, and as well as some other processes which we can fabricate a smaller dimension devices. So, and we will start this course with introduction to modeling and simulation software for MEMS. As I mentioned before, MEMS stands for micro electromechanical systems. So it's about the device or the system that we try to design at the small scale, micro scale, and then what are the software options and how we can do it with some example will be provided. So this will be the content of the course today about the course, introduction to microfabrication and MEMS. Micro and nanoscale, we will look into what is the definition of this. Then we look into Moore's law. I think if you are from the background of electrical, you might be familiar with the Moore's law because it's about more towards electronics, and MEMS application and modeling and simulation for MEMS. So basically, as I mentioned before, the course will provide the participant with a sound understanding of the technique and technologies involved in fabrication of micro devices and MEMS. In some parts of the world, you call it micro device. In Europe, for example, they call it micro fabrication or micro device. But in Japan, in particular, they call it MEMS. And it will also provide insight to the current state of the art of micro technology application. Further tools for design and simulation of micro fabrication and micro device will be introduced. So if you see this figure, this is just an introduction to for you to have some insight, some early introduction of micro devices. So when we talk about thin film here, it's about nano or micro scale. The thickness in micro, maybe I will show you what is the dimension actually when we talk about nano and micro in comparison with the things that we can see with naked eye. So you see that this kind of devices need to be designed and fabricated and integrated in a different way of what we used to think of when we have things at macro scale. Normal mechanical engineer would think of designing and developing such a device. So just a little bit quick introduction. For example, a microfabrication of a process of a crafting minute structure of a microscale, often used, as I mentioned, semiconductor process and MEMS manufacturing. So for example, in this case, you want to have this kind of 20 micron, this is the scale of 20 micron trench. So normally, if you are a mechanical engineer, you would kind of dicing or milling using two tips to make this kind of thing. But it's impossible if you want to get it at 20 micron, right? So you cannot prepare tips of less than 20 micron. It will break. So with force, it won't work. So you need some other means to remove this material and to form this kind of structure. So this can be done using For example, deep RIE, we call as etching. Deep RIE, a process of using ion bombardment. You shoot ion of gas to remove the material. Some materials have selectivity. For example, you have mass here, it won't etch, it won't remove this material, but it will remove silicon. So with SFX ion, so that is where you can remove this part, but this part is not removed. So this as a mass, but this mass normally polymer materials, for example, then you can get this kind of structure to be formed. If you have question, you can just raise your hand and ask question. All right, this is another example. MEMS are regular mechanical system at a small scale. They are often fabricated using silicon electronic chip technology. So silicon materials as the base material normally, then because you want to have electronics kind of circuit integrate with the material itself. So you have to have a process where the circuitry can be formed on the materials. It's not just about mechanical shape or geometry, but it's about laying the circuit on the device itself. So then you have this kind of etching and photolithography in order for you to get this shape and also to form a kind of circuit, etc. on the materials. MEMS devices are often equipped with different types of transduction mechanism. So it's same as normal devices. You need to make them move, right? So you need motor, for example, to move certain, to make certain machine function. So you cannot have the normal motor or actuation mechanism like pneumatic actuation to this kind of device. So it's almost impossible. So you need to move them different way using different kind of actuator. For example, I've mentioned to you that you have piezoelectric. So you can have piezoelectric to be the motor or actuator to move certain parts of the machine. And you have electrostatic. So using electrostatic force, you can also move, make the things rotate or make the things move. And you can have electromagnetics, etc., in order to actuate or move some nanoscale or microscale components inside the MEMS devices. Okay, as I mentioned, MEMS device can be controlled by an external circuit, allowing the device to respond to environmental changes. So you can have some kind of actuator as well embedded into the MEMS devices. Then later on, when let's say it's respond to heat, it's respond to a light, for example, it can make movement. So that kind of sensitivity towards environment and anything that can make the machine response then can be used as tools to make whatever intended work to be done. Okay, a little bit history of MEMS. The first published reference to advance in the area that is now identified as MEMS began to appear when researchers considered ways to reduce the size of engineering device and system. So it's not from the requirement of having some small things, then MEMS also evolve with the, the concept and the principle. Originally, we want to have a small device so that it become more efficient, for example, rather than the big device. Then you do with precision engineering. So from precision engineering, evolve more towards smaller scale and smaller devices to make it more energy consumption, to lower the energy consumption, for example, or to increase the performance of the device. So you make it smaller and smaller, then with that you get more towards sustainable engineering. So that is part of the philosophy or the initial kind of intention of MEMS. An important influence came from the recognition of new possibilities to do this by using technology and design that in 1930s, it's quite a long time ago, produced an electron microscope. First electron microscope was introduced, but to make electron microscope, you have to have a technology because scanning electron microscope or SEM is very precise and you use a lot of high precision things. Then with that, you need to develop something small in order for you to be able to make things precise. So starting from there, it's evolved, as I mentioned, to do more towards precision thing for military, for aerospace application. So that is where MEMS become to kind of explode in terms of application. And a compelling urgency for miniaturization arose from the needs for robotic system in the new growth area of rocket system, for example. So that is part of it. When the war finally ended, progress made in robotic control system became a stimulant for space research, an area brought into a sharp focus at the newly founded JPL. I think most of us know JPL at the Caltech. Okay, he was Caltech professor physics, Richard Feynman. He wrote an essay called with the title "There's Plenty of Room at the Bottom." So this is his kind of philosophical things of looking into materials and product to be developed at the small scale, in which he pointed out the extraordinary possibilities that would be afforded by building microsystem on the scale of natural framework of the molecular arrays that from metals itself. It is remarkable that Feynman's presentation was made before the general introduction of a technology that could make practical use of room at the bottom. So all these things is about, as I mentioned before, it's about a semiconductor. So it's about IC, integrated circuit, was to appear as the new decade in the 1960s. So I think everyone knows when we talk about chip, now you talk about 2 nano, right? 2 nanometer, Intel introduced. I mean, 3 nano has been introduced, but now TSMC, I think you know TSMC, right? Taiwan semiconductor manufacturing company. So developing mass production for 2 nano circuit line. So that is where we are heading to with this MEMS and microfabrications. So the growth of MEMS was very slow because researchers concentrated their attention to the expanding capabilities and commercial products that could be developed in purely electronic integrated circuits. So the focus was IC design using semiconductor process rather than developing the device itself. Now, if you see that you have a MEMS microphone, right? Your handphone. So MEMS microphone. Even you have your earbud with a MEMS microphone and also speakers, MEMS speakers. So that's kind of device come a little bit later because people have concentrated too much on the integrated circuit itself rather than the device. So, but you can see a lot of device in biomedical application, in electronics application such as speakers and etc. Honeywell Corporation Laboratory incorporated a thin silicon diaphragm into a silicon chip. On the diaphragm, they cleverly configured a Wheatstone bridge of piezoresistor. Pressure sensors made in this way became the first of the earliest micro electromechanical system product developed. So this kind of pressure sensor, when you have a pressure different, push this kind of diaphragm. So with a piezoelectric, you know, when you provide strain to the piezoelectric materials, you can induce electricity. So that electricity is a signal of the change of the pressure. So that is very simple but quite accurate pressure sensor. So this small pressure sensor, later on, you can use quite at a few places. For example, if you have expensive car like Mercedes, you have a pressure sensor in the tire itself. So if it's inflated or anything happened to the tire, the car can react accordingly because of you can always measure the pressure of the tire inside too. Okay, and little bit, I mean, the summary of the overall MEMS devices. So in 1950s, metal sacrificial process has been patented in US patent. Metal sacrificial meaning you have a layer of metal, then you sacrifice it for you to develop certain pattern. Because a certain different material can be removed using different chemical. Okay, so you can etch, we call it etching. So you can remove certain materials, for example, hydrochloric or sulfuric acid with different kind of materials. So using this kind of knowledge of things, you can make a sacrificial layer, for example. You have IC, everything, and then a pressure sensor in 1970s, for example, and you have thermopneumatic valve in late 80s, and polysilicon beams, and you have a lot of IR imager, infrared, right? Infrared imager by Honeywell, polysilicon com drive. Com drive is, I mean, maybe I will introduce you later. It's electrostatic actuation method using com shape. So this is all now with BioMEMS, etc. BioMEMS is a device that related to maybe for human or for animals. You can have sensors, or you can have something to monitor your health condition, or to do some even kind of body instruction materials devices of using BioMEMS. So this is where DRE or deep RE is a process to remove material using ion bombardment, developed in late 1990s. So a lot of RF MEMS, for example, RF is radio frequency, so that's enable our different 3G, 4G, 5G network to be enabled using high frequency domain of things. So using MEMS, you can have a smaller, then you can have higher frequency without damaging the materials itself. So as I mentioned before, let's have a look at how small is nano and micro. So you see here, we are about 1 meter or 2 meters as human. In comparison, we are 1,000, 1,000 times kind of smaller than mountain. Then if you look at N, so 1 millimeter, the size of N, so we are about 1,000 times smaller than, N is between us. So bacteria, then sugar molecule at 1 nano, bacteria is about 1 micron. So if you talk about 2 nano device, right, 2 nano electric circuit, so this is at the molecule level. So arrangement of 2 molecule of sugar is the circuit line. So imagine it's just a contaminant normally we cannot see with naked eye. So even the bacteria is at 1 micrometer. 1 micrometer is 1,000 nano. So this is 1,000 bigger than this size, the bacteria we cannot see with naked eye. So just imagine the 2 nano of circuit line that you can control to fabricate with the spacing accordingly. So just to give you another perspective, our human hair is 50 to 70 micrometer. So we can see with a naked eye, but sometimes for myself, I cannot see. Aging, due to aging, you cannot, you have to wear glasses to see at the maybe one strand of human hair. But just imagine this is 1,000 bigger than the size of the line of your circuit in your handphone. Okay, so that is how small is it, and to provide you perspective that of the scale. And okay, I've mentioned about Mohs law. Mohs law is describe the empirical regularity that the number of transistor on the integrated circuit, the transistor in IC, doubles approximately every 2 years. This development is important for the other aspect of technological progress in computing. So you see that from 1970s is following the trend that predicted by Mohs law to have a double the capacity of integrated circuit in the the size, the density. So now you imagine previously maybe during Professor Sujit time, he has the floppy disk. Floppy disk is this size of what you call it, storage. You put in your computer, then it's just how many bytes? About a few bytes only. So now you have your thumb drive with this size that you can store maybe 1 gig, right? 1 gig is normal, 1 gigabyte. So that is, you see how things can be made smaller and increase the capacity. It's not just you increase the capacity, but the size become bigger. But it's the other way around. The size becomes smaller, but the capacity also increase. So that is the computing power that predicted by Mohs law because of the development of transistor density in the for every inch of the size. So it's still following the Mohs law until now. So in terms of application, so we have mentioned about MEMS application. We have a lot of MEMS accelerometer in our handphone. So this accelerometer basically is an initial sensing. You can know your position. That's why when you rotate your phone, it can rotate the screen, and you know your GPS position, where you are now, very accurately, and you know your altitude as well. So that is, use of the MEMS gyroscope or accelerometer. We have a projector for micro display. So I think you have seen in some device you can display project some video or image on the wall using small devices as well. Then for biological and medical devices, you have this kind of, normally in this kind, we have microfluidic sensor. You make a very small microfluidic disc, for example, then with a rotation, you can mix the biology substances with a chemical to detect something. And also you can measure, this is kind of cantilever. You can measure one molecule of things. You get the feedback from your measurement of very precise molecule. So you can measure the heat even of a molecule, or you can measure the weight of a molecule using this kind of cantilever. So it depends on the materials and principle you are using. Then for fuel cell, you have a membrane, for example, to fabricate the membrane, and the electrode for fuel cell, and RF MEMS, as I mentioned. So you have a very small devices now with a high frequency 5G, 6G coming. Then you have a pressure sensor, as I mentioned, in tire, in microphone, printer head. We will see some example later on during our case study for MEMS application in detail. So this is just to provide a quick glance of MEMS application. Let's say you have this inkjet printing head. With this inkjet printing head, you have a small nozzle, a few nano, or it depends, a few microns. For example, here with resolution of 1200 dpi, so this is about 21 micrometer nozzle. So you use resistant heater. So with this resistant heater, basically you expand the when you heat up here at here, then this fluid or this liquid will be expand, or I mean, due to heat, it will expand. Then you can have a drop of the ink injected from here. So this is kind of course, you have different types of inject head. You can use piezoelectric, for example, with the as an actuator. So just to give a quick market for the MEMS, is about in 2024 it's nearly US 20 million here for MEMS, inject heads, gyroscope. I mean, a few segments, but the total is about 20 million USD. So, and we are dealing in the next 50 years, you know, the SDG, UN Sustainable Development Goal. We are predicted to have a kind of to address these issues of energy because of the population, increase in population. We have to look into water security, food security, environmental issues, poverty, terrorism and war, disease, education, democracy, population, etc. But some of these can be addressed by using less materials. If we use MEMS technology with a micro scale devices, we can use less material instead of using a big bulk material to have some devices at the big scale. Skip this one. Okay. Then we look into the modeling and simulation for MEMS. I think some of you become sleepy. It's just me talking. Any questions so far? No? Everything good? Okay. So shall I continue? Okay. So modeling, it is quite common in every field of engineering. We try to do simulation and modeling before we start with the experiment or building the actual thing. So this will save the cost and save a lot of times fail building. If it's failed, then we try to predict the performance and predict the properties by simulation. So in MEMS, we can do simulation. Microelectromechanical system is a process technology that combines mechanical and electrical components to make micro-scale range devices. And a considerable cost of the device can be reduced if we simulate the design. It's the same thing as some other things as well. There are many available simulation software to choose from, which in turn is one of the major challenges. So if the design involves specific physics, geometry, materials, or meshing, the search must be done to find appropriate software, because some software has limitation. You can simulate at a micro scale, or you can simulate at macro scale, but the thing is, at the micro and nano scale, things does not follow Newtonian mechanics. So you have to have a little bit different or integration of kind of maybe quantum mechanics or some other I'm not well versed in this, but somehow the Newtonian mechanics for macro scale will not provide you the accurate prediction. So that is where you need to carefully look into some software which can do this kind of things. If the user intends to fabricate the device, then software with a virtual fabrication tools need to be selected as well. So you have the process simulation as well for MEMS, but that is secondary stage. But firstly, when you design something, you want to know the performance, right? The device performance. So when you get the device design. So MEMS simulation phase, pre-processing, external interface, then MEMS software. Then you have software to do analysis with the MEMS software. Then you have post-processing, external interface, and result display. So this is quite similar to what we have with the common material, common software, process. Some commonly used software for creating geometry, such as MATCAD, AutoCAD, Vectorworks, and Layout Editor. And some key software used for MEMS simulation are ANSYS. If you are anyone using ANSYS so far, no? Okay, you familiar with ANSYS? Okay, good. And you can use COMSOL, okay, and Sugar, Conventor, IntelliSuite. So these are quite commonly used MEMS software, software to simulate MEMS. So this follow quite common in many design process. So you have your layout of the, you have requirement first. So with system requirement and specification, this is just a normal product design process with you identify requirements, identify what a user needs, etc., and what specification should be included in the product. Then you go in at the system level design and integrate, try to include everything. Then you provide the geometrical design of the sensing element, for example. Then you design of the signal evaluation part. So because normally MEMS will have one is about the feedback and the signal, and the other is on the physical of the or the geometry of the product. Then you have your mechanical layout and you have electronic layout. And some device, you integrate everything, but some you have you just provide the electronic layout or the circuit layout on the MEMS devices. Then you control everything at the other, integrate electronic parts. Then you have your overall layout here. So this is kind of general process of designing MEMS device. And for example, this is a micro positioning stage. So if you see here, simulation using ANSYS, and you have a stage. This is the center stage. So because this stage intended for X and Y direction, you make with this system inside, you make the direction of Y, and the X is here. So everything will move on the X direction. This is the whole stage, and this is the inner stage, outer stage. So the thing is, you need to provide actuation. How to... Actually, there is a kind of animation for this. I'm not sure. Okay, you can see that you can move for both direction X and Y. So you can simulate this using ANSYS. And this has been done by providing force at this, because this place intended to have actuator, so piezoelectric. So it expands here. When the piezoelectric actuator is located here, then you can have the expansion of the displacement of piezoelectric. Then it will push these two sides. Then this stage will move to the right, and the same here. So that is the piezoelectric actuator with a MEMS. Of course, this simulation intended to measure how far you can move the stage of X and Y direction, and how much force you need to exert, you need to put on this both sides, meaning to say it will provide you some specification or requirement for you to design the actuator as well. Okay, apart from that, if you see here, there is a hinge at every place, because this hinge will provide the flexibility to move, to make a movement of this stage, for example. Then you can also simulate this hinge itself in order for you to get the right design and the right range, hinge size, for example. So when the input of the force here, so how much will this displacement happen? So the displacement of this will provide the displacement of this side. Okay, so this the design of the hinge will be critical in order for you to make sure that it will be able to move, and at a certain extent you have the robustness to hold the loading of the stage on the stage itself. So it can be done through calculation, numerical calculation, and it can also be done by simulation. So if you do simulation, for example, you can get the relationship between displacement and the force. So force force on this direction, meaning how much that you can supply the force to make the movement. So because you have to overcome some other spring issues as well. So this is a kind of simulation that can be done in using ANSYS for MEMS simulation. And this is the actuator that you put in between. So you can do the simulation and get the relationship between, let's say this is FEM, the simulation using ANSYS. So you can see that the angle here is very important in order for you to have a amplification factor. So this Moni structure basically can amplify the force, and also can amplify the movement, the displacement. So with a small displacement, you can amplify it a few times. For example, here you amplify up to nearly 20 times. So if your actuator can only make 2 micrometer, here, for example, with a 2 micrometer, you can get here nearly 40 micrometer. Okay, with a 2 micrometer movement, you can get nearly, 2 micrometer on this movement, you can get this delta M up to 40 micrometer. So that is a very long, huge amplification. So another simulation, another things that has been simulated using for this design is on the stiffness of the spring here. So you have a spring mechanism, then you need to make sure that this spring is not that stiff until you cannot make the movement. But at a certain extent, you have to maintain the robustness of the spring to withhold the stage, because the stage also you have some mass. So the mass of the stage, then you need to make sure that this spring can withstand, and also at a certain extent flexible enough to make sure that the movement can be done. So this, let's say this is just trial and error with a 50 micrometer thickness of the spring, then you can simulate, then you can change the dimension to maybe 60 to see how much force is required in order for you to make sure that the movement can be done by these systems. For example, here, and with this spring of, you can have a force of up to 1 Newton, then this displacement up to 10 This is meter times to the power of minus 3. Okay. So meaning the support spring stiffness for the two support spring is predicted to be 99.5 Newton per meter. So this is another MEMS simulation using ANSYS. So almost the same thing, but of course, I would like to show you kind of the layout of the example of using the ANSYS. I think the file is here. It's not linked. Let me see. Which one? Is it this one? Ah, okay. Oh, sorry. Okay. Okay, this is, I mean, if for those who are not familiar with ANSYS, so you can see the interface of ANSYS, and basically you can design here, and then you can simulate and kind of include the properties of the materials, etc. Then you do the processing of the design. Okay, this is kind of cantilever. Then with a pre-processing. Okay, it's quite it's not that difficult for those who are quite familiar with the software. Then you basically tutorial for designing MEMS, etc. is available for each software. Even you use IntelliSuite or you use ANSYS or you use COMSOL, there are many tutorials that you can learn from the company itself, from the website of the company. You can learn on how to use with a certain design. But of course, if you have different design, you just follow the steps. But you can have your own design. Okay, just skip it. Okay, and next is on the COMSOL. You have an example of COMSOL as well. You click, yeah. Can you open? Yeah, yeah. That's in the folder. You open the folder. COMSOL. Where is COMSOL? Conventor. Maybe this one is COMSOL. Yeah, I think. Yeah, yeah. Just keep go to a few minutes.
Hello everyone. HF works, which is used for electromagnetic.
We have seen maybe few years on these issues. Now let's have a look on some challenges posed by MEMS applications.
And sometimes we can integrate. I mean, the model. We can create the model in SolidWorks, and we can export the model or import the model into ANSYS or COMSOL to do further simulation of multi-physics. So you can do in that way as well of using this kind of software. So you do geometric modeling using SolidWorks. Even in SolidWorks, at certain extent, you can do the MEMS simulation nowadays.
The use of different materials options versus the output results to get the right and the optimal behavior of their devices. This includes different material types, anisotropic
Okay, just to get you to know a few things. Okay, and this is using IntelliSuite. Maybe you can show the interface of IntelliSuite. Yeah. The link won't work, is it?
materials, temperature depending materials. For this reason,
This one
EMS
video.
came
This
with
one video.
a rich
IntelliSuite. Converter, yeah, this one.
So let's start the design of a comb drive structure. Here I've created 2 layers. One
So
is
this
comb
is
and pads.
IntelliSuite.
So here I create them by adding new layers, and I can change the color here.
Okay. Maybe you
So
can skip a few
the
minutes.
idea of changing the
Just
color
to
is to
show
differentiate
how
between the layers. So
it can be used.
we can as well hit it. So 25 to escape. So this enables 90. So it's on the y-axis. So here I select layer fill.
Nothing.
So to have
this
a
is
clear look,
I mean,
and go to
the modeling.
create rectangle.
Then you do the simulation. Maybe at the center. I mean, halfway. Okay. This is COM drive basically. COM drive is electrostatic actuator. So this is. Okay, how you design, then you do the simulation for the COM drive. Okay, so then you apply electrostatic force. Then we see later on the movement can be simulated on how much you can make the movement due to electrostatic force on this COM drive. COM drive can be used as an actuator and also as a sensor as well. So it's bifunctional. Maybe you can forward. Yeah. Okay. See some animation. So basically, this part is a kind of anchor. And of course, for COM drive, you have to have a circuit line on this. So that is where the process, the MEMS process is complicated. It's not just structural things, but you have to have electrical simulation as well. So to provide the capacitance here, capacitive sensor, and the electrostatic force to this area, then you have to have your circuit line go pass through on the surface of this material. You can see that we can make a movement of this. Okay, so that is a COM drive simulation basically. Right. So thank you. Okay, this is using converter example. So I think this is just the interface of the converter as we can be seen here. So we can do the same thing as well. I mean, the MEMS simulation using electrostatic force, and also, I mean, the normally about MEMS actuation is electrostatic or piezoelectric or heating. You have your thermal deflection materials as well, and magnetic. Then you look into force, you look into displacement, and you look into rotation, for example. So a lot of things can be done using MEMS software. And with many software, previously it's quite limited, but now you have a lot of options. You can use console, you can use ANSYS. Even nowadays, you can use SolidWorks at certain extent. So all the multi-physics software can be used to simulate MEMS devices. All right. I think that's all. Thank you. Any question? Are we on time? A bit earlier. I think I'm a little bit earlier, 8 minutes earlier. Any soft? Yeah. Pardon? Yeah, multi-physics software.
Sir,
Yeah.
good afternoon.
Yeah. Afternoon.
Thank you for the wonderful lecture.
Yeah.
Really, we enjoyed it. Okay, many very interesting information was there in your slide. Okay, then coming to my question, we have some multi-physics software is there. Like for example, in welding,
Okay.
we use same console multi-physics.
Okay. Yeah.
But from your lecture, we came to know that we can same software we can use for the MEMS simulation also. Is it same software or it is different?
Yeah, it's same software, multi-physics console, right?
Okay.
Yeah, same software.
So then here, what kind of like heat flow you will apply? There welding means we know the thermal cycle, we know some deformation type of thing.
Yes.
But here, what will be the input from your end?
Voltage?
Input,
Then,
yeah.
yeah. I mean, you apply current.
Okay.
It's the same thing. It's just that different scale.
Okay,
Yeah.
but scale different.
Yeah.
Okay, sir.
So you might be applying for your case welding. You apply maybe potential and a very high current, right?
Yes, sir.
So
Yes.
this
Yes.
is at maybe nano or micro
Okay.
ampere.
That means that
Yeah.
insignificant deformation we can note down here.
Yes.
Is it, sir?
Yes.
Okay. Okay.
So it's depend on the materials and also, yeah, but the thing is, the software is very smart now. I mean, even though you are talking about the multi-physics that at macro scale of welding, but now when you change your scale at the micro scale, as I mentioned before, it won't be the same as it won't follow the Newtonian mechanics. The software can do that nowadays. I mean, it can. I mean, when you switch to different scale, so they don't really look into. They can integrate between Newtonian and the quantum mechanics of things in order to simulate at the micro scale. Any other question? Yes.
In those simulation for materials, how can you change, sir? For resistor, you are telling, sir, like spring.
Okay.
There will be multi-materials.
Yeah. I mean, you have a different layer of materials,
Yeah.
right?
Those
normally.
parameters we can.
So
change.
you
It's
can
complex.
change the material properties. Basically, what material you are using. So let's say you are using gold as the circuit line. Then you have your silicon. So the silicon also you have a direction, right? So everything can be defined in the process before. Define the material before you do processing. So you define the material, you get the material properties right. The material properties can be defined in very detail. So Young modulus, for example, Poisson ratio, etc. You include that. Not just select the material, but you can have your own materials. It's not just selection from the library.
Okay.
Yeah.
Thank you, Professor. I will add some point in this question.
Yeah.
His doubt is he is working on MTech project. He want to fabricate some composite. For example, copper as a parent material. He is going to give some filler addition of some nanoparticle to make a one copper-based composite through friction stir technology, friction stir welding. So he done the modeling in the copper, but incorporation of that nanoparticle, he is facing a lot of challenges because he is telling, sir, I'm not able to choose the particular material because it is not in the library, material library. Can you light on
I
this?
think okay. I'm not so sure about I mean the behavior of the material to be simulated in this kind of software, but I know there is a website called Materials Project. That material project website, you can kind of simulate the property of the material when you mix with something. But now you are talking about physical properties for the mechanical application. Let's say the young modulus or the hardness or the strength. Perhaps it can simulate that as well because the materials project is about the physical properties of electronics application. Yeah, normally. So maybe you can explore that materials project website.
Okay. Yeah. Thanks. Thank you, sir.
Yeah. Okay. Any other question? It's okay. Okay, okay. Thank you. All right. Thank you very much. What time now?
I have put the watch here.